Hello students, this is lecture 20 of MTH 201. In the last lecture we discussed double integral over a rectangle and a general domain, iterated integrals, and we discussed Fubini's theorem. Okay, so in R2 we can define two kinds of elementary regions. So let us see what these elementary regions are. So let phi1 and phi2 be two functions from closed interval ab to r which are continuous and phi1 is less than or equal to phi2 for all x in the interval a comma b. A subset D of R2 defined as the collection of all the points x comma y in R2 which lie between phi1x and phi2x as x varies over the interval a comma b. Such a set is called a region of type 1. Okay. So if you look at these pictures here, we have two functions phi1 and phi2, right? One is below another. Now you vary x over a to b interval and you let the y coordinate go from phi1x to phi2x, right? So in these three pictures, the shaded region is basically the region that we are talking about, and such are called type 1 regions. Then we have type 2 regions where you have two functions psi1 and psi2 from closed interval CD to R which are continuous and phi1 is, this should be psi1 and psi1 is less than or equal to psi2 for all y between C and D. Then a subset D which is the collection of all the points in R2 such that the x coordinate lies between psi1y and psi2y and y coordinate varies from C to D is said to be of type 2. Now, if you look at these three pictures, that's what is happening, right? You have two functions which are from closed interval CD to R. So, these are their graphs and you let y goes from C to D and x goes from psi1y to psi2y. So, these shaded regions are all type 2 regions. Okay. Now there is a third kind of region which is called type 3 and a region is said to be of type 3 if it is both of type 1 and type 2. So you can find phi1 and phi2 such that the region looks like type 1 or you can find psi1 and psi2 such that the region looks like of type 2. So if you take this circle, right, circular disc, then in this case it is both, it is type 1 as well as type 2. Why is it type 1? Because you can think of this region as x going from -1 to 1 and y going from phi1x to phi2x, where phi1x is the bottom part of this circle which is negative square root 1 minus x square and phi2x is the positive part of this circle which is square root 1 minus x square. So with this notation, it is a type 1 region. Similarly, you can write it as a type 2 region where you define psi1 and psi2 as follows. So now you take the left side of the curve, that is minus square root 1 minus y square, and the right side of the curve of the circle is square root 1 minus y square. So with this notation, it is a type 2 region. So there are three kinds, type 1, type 2 and type 3. If a region is both of type 1 and type 2, then it is called a region of type 3. Okay. So there is this result which we are going to look at without a proof. It says that if you have a continuous function over an elementary region D in R2, then it is integrable on R2 on D. and we have Fubini's theorem in this case, which tells you, so remember we did Fubini's theorem for a rectangle in the last lecture. Now we are going to talk about Fubini's theorem for a function which is defined on an elementary region, right? So let f goes from D to R be a bounded function over an elementary region D. Does it matter whether it's of type 1, type 2 or type 3? And let D be contained in some rectangle, okay, which is R equal to AB cross CD. Then if D is of type 1, then now we defined last time that we defined integral, double integral of a function over a general domain to be double integral of this should be f tilde, okay. So double integral of the extended function f tilde over the rectangle, and so this is something that we did last time, right? It comes from the definition, that's okay. But how do you compute this integral? It's nothing but, now x varies from a to b and y varies from phi 1x to phi 2x, right? So you integrate this function accordingly. If D is of type 2, then your y varies from C to D and x varies from psi 1y to psi 2y. So remember that the innermost integral is corresponding to the innermost D, the infinitesimal variable that you see, right, which is dx. So it's the same order, right? You start from inside and then you move outside, okay? And then if D is of type 3, then anything would work because you will have phi 1, phi 2 as well as psi 1, psi 2, right? So any of the integrals would work. Okay. Now let us look at a few examples. So calculate the integral of this function over the region D shown below. So D is this region. Okay. Now you can easily see that it is a type 1 region, but it's not a type 2 region. I will leave that to you. So you can find phi 1 and phi 2 as shown in the figure, but you can't find psi 1 and psi 2 so that it is of type 2. Okay. Now since f is a continuous function on D, it is integrable over D. D is an elementary region. So we can apply Fubini's theorem. What is phi 1 here? Phi 1 is the line segment joining 0, 0 and 2, 2. So phi 1 is going from closed interval 0 to R and defined as phi 1 x equal to x. That will give you this line segment. And phi 2 is this above line segment, which is the line segment joining 0, 1 and 2, 2. You can compute that it is nothing but phi 2 going from 0 to R, and phi 2x is x by 2 plus 1, whose graph is this line segment. So now we have written down our domain as a type 1 region, right? Now from Fubini's theorem, integral of this function over D is nothing but, now you take the x limit which is going from 0 to 2 and y limit goes from phi 1x to phi 2x. So phi 1x is x, phi 2x is x by 2 plus 1. Integrate the function dy dx. Now I will go through these steps quickly. These are just computations. So as I said last time, you start from the innermost integral. So in the innermost integral, x is treated like a constant and y is varying. So you integrate this function over y, you get this, and your limits are x to x by 2 plus 1. You put in the limits, you get these two terms. This is the term you get from the upper limit substitution. This is the lower limit. Now this is a function of, this is like one variable integral, you know how to compute. So rest is all the computations. I will not go over these computations. Okay. Let us look at another example. So in this example, So in the example on the previous slide, express the integral over d as an integral or a sum of integrals of the form dx dy. Now if I go back slide, here we wrote down it as dy dx because it was a type 1 region. Now let us see how we can do it as dx dy. So you can write this region D as a union of two regions. One is D1, other is D2. Okay. And you want dx dy, which means that you want to write it as a type 2 region. But you notice here that both D1 and D2 are type 2 regions. And how? If you look at D1, the lower, so y goes from 0 to 1 and x goes from 0, which is this line, to x equal to y, right? So x goes from 0 to y. Now for D2, y goes from 1 to 2, right? And x goes from this curve to this curve. What is this curve? This is 2y minus 1 and this curve is y, right? And that's what I have written here. So now it's easy. What is this integral? It's the sum of these two integrals, right? And first integral comes out to be this using, because D1 is a type 2 region, and similarly because D2 is a type 2 region, you get the second integral. And then you can just solve these integrals. And because we, in the last slide, we already computed this integral, whatever answer you get here should match with what you got on the previous slide. So I will leave that to you. Okay. So even though this region D was not a type 2 region, we were able to break D into two regions, both of type 2, and still apply Fubini's theorem. Okay. Now let us look at another example. So evaluate this integral. Identify the region D such that this iterated integral equals the double integral of the function over D. So you have to basically see which region D would give you such limits. Now what is D region? D region is x varies from 0 to 1 and y varies from x cube to x square, right? So this is my region and you can plot it and this is what you get. This shaded region is D region. So the bottom curve is y equal to x cube and the top curve is y equal to x square and y lies between these two curves for a fixed value of x. So this is my shaded region. Now y equal to x cube can also be written as x equal to y to the 1/3 and y equal to x square can also be written as x equal to y to the half, right? So if we think of D now, in this particular case, D is a type 3 region. It is both of type 1 and type 2. So if you think of it as a type 1 region, then you can compute it this way. You will get dy dx and the limits, right? That's what you were asked. But you can also look at it as a type 2 region, in which case y goes from 0 to 1 and x goes from y to the half to y to the 1/3, which is what I have done here. If you do all the computations, you have to get the same answer, right? Because xy is a continuous function. So it is satisfying the hypothesis of Fubini's theorem. Okay, so remember one thing, that when you compute such integrals, you start from the innermost. Innermost is with respect to y, so x is a constant, and then you move out. Okay. Okay. So now let us, we have looked at a couple of examples. Now let us move further. So let us now talk about mean value theorem for integrals. So for single variable, you have you know that if you have a function from closed interval ab to r which is continuous, then there exists a point x naught in AB such that f of x naught is 1 by b minus a integral a to b fx dx. So this is also called average of the function and it is attained at a point. Okay. Now for double integral we have a similar result when your domain is an elementary region. Okay. So let D be an elementary region in R2 and f goes from D to R be a continuous function, then there exists a point x naught y naught in the domain such that f of x naught y naught is 1 by the area of the domain, which is an elementary region, double integral of f over d. It looks the same as for one variable. Now your function is of two variables. Integral becomes double integral. B minus a here is the length of the interval. Here you get area of the domain. Okay. So how do you compute AD? How do you compute area of D? So if D is a type 1 region, then its area is nothing but, now x goes from A to B and y goes from phi 1x to phi 2x, right? So this is the area. If D is of type 2, then y goes from C to D and x goes from psi 1x to psi 2y. So this is the height, right? So this is what you get. And if it's of type 3, then you know any of the integrals would work. And the idea of the proof of mean value theorem for double integrals is similar to that of single integral. So we'll not get into the proof of this. Okay, let us look at this example. So suppose your rectangle R is this. We want to prove that this double integral over this rectangle is between 1 and 6. So let us look at this function which is 1 by x square plus y square plus 1. Now this function attains absolute minima at 0, 0 and absolute maxima at 1, 2 in the domain. So here I would like you to check that this is actually the case. Okay. So how do you do that? You find out the critical points, then you look at the boundary and you find absolute maxima and minima. So this I will leave to you. So therefore fxy in this domain is less than f00, which is uh, just a minute. So this should be opposite, right? This should be maxima at 0, 0 and minima at 1, 2. Okay. So therefore f00 is greater than or equal to fxy and that's greater than or equal to f1, 2. And at 0, 0 value is 1, at 1, 2 value is 1, 6. So this is the relationship you get. Now you take double integral on all the sides. So you get this. Okay. Now what is this integral, double integral over R of constant function 1 dx dy? It's nothing but the area of R. And on this side you get 1 by 6 times area of R and this is the integral that is in hand. Now what is area of R? It's a rectangle. Area is easy to compute. It's length times height. Length times breadth. So length is 2, breadth is 3. So your area is 6. Then you plug in the values, you get what you wanted. Okay. So now we will move to triple integrals. So we have already looked at how to integrate functions of two variables. Now let us move on to integrated functions of three variables. Okay, so we described double integrals as area under the graph of the function above the domain, right? Now in R3, that description is no longer intuitive. Why? Because Now your domain is sitting inside R3. It's a function of three variables. So when you look at the value of the function, you will need R4 to visualize it, which we don't know. So we don't know how to make sense of that, whether we can have that kind of geometrical interpretation. So, but there is still, these triple integrals are still of use, and they are used in several physical problems. For instance, if the temperature in an oven is not uniform, we find the average temperature in the oven by summing the values of temperature function at all the points in the solid enclosed by the walls of the oven. And then we divide by the volume of the oven. Such a sum can be expressed as a triple integral. Okay. So triple integrals are mostly used when you want to find average of a function which is defined in a domain which is sitting inside R3. Okay. So it could be average temperature in the room. It could be, if there's a liquid in some beaker, it could be average temperature of the liquid in the room, or things like that. Okay. So what is the procedure? Procedure is very similar to double integrals. Now your function is defined not on a rectangle but on a box. Okay. So what is this notation? It's similar to what we defined for a rectangle. It's the uh, point x comma y comma z, where x lies in this interval, y lies in this interval, and z lies in this third interval. So it's a collection of all those points, and what you get is a box. So what do? You divide each side into equal parts, m and l of these lengths. So this is the pictorial representation. You have a box, you divide it into sub boxes, and each sub box has volume delta x, delta y, delta z. Okay, and I'll denote each box by B, I, J, K. Now you take a point in the box, you define triple integral to be, now there is a triple sum because all of I, J, K are all varying. You evaluate it at the point times the volume of that box, right? So we say that this triple integral makes sense if this limit exists and it's independent of the choice of the point. Now what is the limit over? Limit over is the limit over the, so as you let the divisions go to infinity, right? Division of each interval, each side go to infinity. Okay, so it's the same principle. The sum in the definition above is called a triple Riemann sum, and in the Riemann sum we can evaluate f at any point in the sub box. And the term dv, remember in double integral we had dA. Now here we have dv, which is the infinitesimal volume component, and it is also written as dx, dy, dz. Now there are three variables, right? And if the limit exists, we say that f is a triple Riemann integrable function. Properties hold like for double integrals. So all the properties that we saw for double integrals will hold for triple integrals as well. And theorem is that if you have a function from box B to R, which is continuous, then it is Riemann integrable. And triple integrals are computed using iterated integrals with three integrals rather than two as for double integrals. So I would like you to write down all the possible iterated integrals. Remember, in the case of two variables, we got two options, dx and dy. Here you have dx, dy, dz. So you try to figure out how many possible combinations are there. So write down all possible iterated integrals and then write a statement for Fubini's theorem over rectangles, over boxes, right? So this I will leave to you. It will be discussed in the tutorial as well. Okay. So now let us look at elementary regions in R3 like we did elementary regions in R2. So here there are plenty of options. So let D be an elementary region in R2. So you first start with an elementary region in R2 and suppose gamma 1 and gamma 2 are two functions from D to R which are both continuous such that gamma 1 is less than or equal to gamma 2 at all points of D. You define W to be all the points x, y, z in R3 such that z lies between gamma 1 and gamma 2 and xy lies in D. Then W is known as an elementary region in R3. And Fubini's theorem tells you that if f is a bounded function over an elementary region, if D is of type 1, then triple integral over W of f is double integral over D, and then z goes from gamma 1 to gamma 2. But then double integral over D can be written like this, right? Because it's a type 1 region. So this is what you get. Now how would you unsolve it? By starting from inside. From innermost, z is a variable, x and y are constants. So then you move out and out. So you start from the innermost integral and then move out. Similarly, if D is of type 2, then this is what you get. Okay. So in type 1, you will get dz, dy, dx. Type 2, you'll get dz, dy, dx. And if D is of type 3, then obviously any of the above integrals would work. As I said, there are several possibilities of elementary regions in R3, and these are all the some of the possibilities. So in the first one, your top and bottom are functions of x and y, like we defined in the previous slide. But then you can have front and back, right, which are functions of y and z according to the axis. Or you can have left and right, which are functions of x and z. So I will leave this to you to think over. We will discuss this more in the tutorial. Now this is a sphere and it is actually of all types, so that you can check. I will leave this as well for the tutorial. I'm not focusing too much on this part. The idea is that triple integrals are very much like double integrals. It's just that you have one more term, right? And they are solved using iterated integrals. Okay, let us look at this example. So let W be the region bounded by the planes x equal to 0, which is yz plane, right? Which is this plane at the on the screen, and then y equal to 0, which is xz plane, which is this left plane, and z equal to 2, right? Z equal to 2 is this plane, which is the dark black plane, and the surface z equal to x square plus y square, which is this surface, right? So basically the region that I am looking at is this inside solid region, right? And so you can think of it as integrating, it's like an elementary region, right? Where D, which is this, is an elementary region in R2, and Z goes from x square plus y square to 2, right? So you can describe W as this collection where x goes from 0 to square root 2, y goes from 0 to square root 2 minus x square, and z goes from this bottom surface, which is x square plus y square, to the height, which is 2. With this description, your triple integral would be like this. Now z is in terms of x and y, so it has to come in the middle. Then y is in terms of x, so it has to come next. And then x limits are constant, so it is outside, right? Now, if you think of it differently as this, Okay, so let's look at the second picture. In this, z goes from 0 to 2 and y goes from, so y is this side, it goes from 0 to square root z, and x is this side which goes from 0 to square root z minus y square, right? Because it goes from 0 to this graph, right? This graph is basically z equal to x square plus y square. So what is x? X is square root z minus y square, this top one. Now if you use this, then triple integral would come out to be this. So this again you can solve these two integrals, answer should come out to be the same because we have just described w differently in this case. Okay, so there is some geometry involved and one has to really draw a picture and figure out what the limits should be. But keep in mind that outermost limit can't be in terms of variables. Because then when you integrate it, you won't get a scalar, you will get a function. So outermost is always constant limit. Then the second one is in terms of the previous variable, which is outside, and the innermost can be in terms of the outermost two. That's how it works. Okay. So let us stop here.